Hello, welcome back to your chemistry class, and I hope that you are enjoying your break here, your holiday break. And I also hope that you've taken a look at the chapter. We're going to be starting with section 8.4 and going to the end of the chapter here. So hopefully you've at least skimmed it. If you haven't, why don't you take a minute to do that here, stop the video, and then come back after you've skimmed that section so you know what we're going to be going over, and you kind of prime your brain for that. Now, last time we were looking at thermochemical equations. That's how we ended. And we were looking at this famous reaction that Antoine Lavoisier borrowed from Joseph Priestley, in which he decomposed mercury 2 oxide to make liquid mercury and oxygen gas. And this process absorbed energy. 182 kilojoules of energy were absorbed for every 2 moles of mercury 2 oxide that was decomposed. And Lavoisier supplied this with a large lens that he shined on the mercury 2 oxide in a sealed container and then heated it up. Now, there's a couple things I want to talk about before we move on with the 3 rules of thermochemistry. And those are some different, I guess you could call them kinds of delta H's. This sort of delta H here might be called delta H of reaction. You might also see one for, if this were a combustion reaction, you might see this delta H of combustion. So, for example, you'll find tables that list the so-called heats of combustion for various compounds, maybe different alkanes like propane and butane and hexane. You might see that around, and again, this would be called the heat of combustion. You might see this symbol, delta H SOLN, and that would be the heat of solution. And that would simply be the delta H that is absorbed or released during the process of solution of a compound, so when a compound dissolves. Now, typically these are going to be listed in terms of kilojoules per mole. So if heat of combustion, for example, well, heat of combustion and heat of solution are going to be in terms of kilojoules per mole. They will be, for example, you might see something like sodium chloride, and you might see its heat of solution listed in terms of kilojoules per mole of sodium chloride. Heat of combustion might be listed in kilojoules per mole of propane. A couple other important forms of delta H are delta H of vaporization and delta H of fusion. Delta H of vaporization is the heat released when, or heat absorbed, when 1 mole of a substance goes from a liquid to a gas. That's vaporization. And fusion is the heat absorbed when 1 mole of a substance goes from a solid to a liquid. So just to give you an example, delta H of vaporization for H2O is 40.7 kilojoules per mole. And then delta H of fusion for H2O is about 6.00 kilojoules per mole. So it takes quite a bit more heat energy to vaporize water than it does to melt ice. But these are some of the types of delta H's that you'll see around, and we'll be using them on and off as we move on in the chapter. Okay, so moving on from there, we have the rules of thermochemistry. These are 3 rules that you're going to be using in solving the various types of problems that we'll be doing. And the first, rule number 1, is that delta H is directly proportional to the amount of reactants or products. And you can kind of see that hinted at here. The fact that these delta H's are listed in kilojoules per mole is telling us this, that this is proportional to the amount of It's going to be affected by the amount of stuff that's reacting. And look up here, we can see the same thing here. Remember, we said that this number plus 182 kilojoules was for a specific amount of mercury 2 oxide decomposing. So, for example, when 1 mole of ice melts, 6.00 kilojoules of heat is absorbed. If 1 gram of ice melts, how much heat is absorbed? So let's take a look at that. What about if 1 gram of ice melts? Well, here's how we'll take that. First, we've got to convert to moles. And I'll bet you're glad to see the mole again after a break for a couple of chapters. Molar mass of water, 18.02 grams per mole. Now we're going to take this, the heat of fusion, because we're melting it, so. Alright, and if we run those numbers, we get 0.333 kilojoules. So because we're not melting a whole mole of ice is 18 grams, it only takes 0.333 kilojoules to melt that. Let's look at another example. Reaction of hydrogen gas with chlorine gas to produce hydrogen chloride. Delta H for that reaction, as it's written, is negative 185 kilojoules. Now the question says, when 1 gram of chlorine reacts, what happens in terms of heat? Again, we're going to start the same way. We're using the factor label method here. 1 gram of chlorine, 1 mole of chlorine, 70.90 grams of chlorine, negative 185 kilojoules. Remember, the negative simply indicates that the heat is being released. There's no actual subtraction that's going to be going on here or anything. And this comes out to negative 2.61 kilojoules. Now notice, I'm not going to write kilojoules per mole in this case. The moles canceled out here. This is kilojoules that are released from 1 gram. So that's the first rule. Just remember that the heat absorbed or released depends on how much of the substance is reacting or melting, whatever it is. It's proportional to the amount. Rule number 2. So rule of thermochemistry number 2. Delta H for a reaction or a process, could be a physical process as well, is equal in magnitude but opposite in sign for the reverse reaction. So we have something like this. When we're melting water, going from a solid to a liquid, delta H for that process is positive 6 kilojoules. Heat is absorbed by the process. That is, the melting ice cube is absorbing heat. If you're holding that ice cube in your hand, it's taking heat from your hand, and your hand is getting colder. If you're melting that ice cube in a pan, for example, then the pan is going to be getting colder. But if we reverse that process, so in other words, we're going to go from a liquid to a solid, so we're going to run the same reaction backwards, and by the way, this is all 1 mole of water. Then delta H is going to be exactly the same in magnitude, but opposite in sign. So heat is going to be released. Now this is a little strange. It may seem a little strange to you that when water freezes, it actually releases heat, but that is true. It actually releases a little bit of heat when it freezes. And there's a famous kind of situation that I like to talk about when we are discussing the heat of fusion. By the way, this is the heat of fusion for water right here. Is Dr. Bent, who many of you probably know. He lives in a drafty old house, and the basement's like a stone foundation, and so it's really drafty, and a lot of times he'll have problems with his pipes freezing when it gets really cold. And so he figured out a method that he was going to try. So this is his drafty old basement, and what he did is he took a kiddie pool of water. He put a kiddie pool down there, and he filled it with water. And what he figured is that as the water froze, so as it gets down, when it gets to 0 degrees C, the water is going to freeze. And then as the water's freezing, it's going to release heat to the surrounding as it's freezing, which should help to moderate the temperature at 0, or help to keep the temperature steady at 0 degrees C. There's something that you should watch a video that I posted up on Moodle, which is called the heating curve of water, and it looks something like this. As you add heat to water, you start off with, say, cold ice. Maybe this is minus 20 degrees C or something like that, and then when it gets up to 0 degrees C, so here's our temperature, this is the heat we've added on the x-axis. Once water gets up to 0, then it will stay at 0 until all the water's frozen, until all the water is, if this is ice and you're heating up the ice, it'll start to melt at 0, and it'll stay at 0 as long as there's some ice present, if it's a well-mixed mixture of liquid and solid water. But then once it's all liquid, it will start to warm up again if you continue to add heat. And as you get up to the boiling temp, then as the water's boiling, it's going to remain at 100 degrees C, or thereabouts, depending on the pressure and the purity of the water and stuff. It's going to be 100 degrees C, but it's going to stay at a steady temperature as it's boiling until it's all steam. At that point, you can continue to heat the steam up as hot as you want. All right? And this amount right here, this is our 40.7 kilojoules per mole. And this amount here is our 6 kilojoules per mole. Now imagine this though, if we're going backwards. So Dr. Bent, let's say he puts in some water, and let's just say maybe it even starts here at 0 degrees C, but it's all liquid. What he was hoping is that as it was freezing, it would be releasing all this heat to his basement, so that it would help to keep the basement from going below 0 degrees C. And indeed, it would do that, except the problem is, of course, it's not an infinite source of heat. At some point, once it's all frozen, it's going to stop releasing heat, and then the basement can certainly cool below 0. It might delay the process a little bit, and this, in fact, is what he found. I believe he actually tried it, and it didn't work that well. Of course, the other problem was he's got a constant influx of cold air coming in here to actually keep removing, and of course heat can actually leave here too, so heat can leave as warm air, and then cold air can come in. So it didn't work that well. But since then he's read that this sort of thing was done in say in colonial times, and in old times people would put barrels of water into storage basements and root cellars and that sort of thing to try to keep things from freezing. So that's the second rule of thermochemistry. And by the way, it works for chemical reactions as well. If you reverse the chemical reaction, you simply change the sign of delta H. Rule number 3. Rule number 3, we start to get a little bit more involved. The first two rules are pretty straightforward. Rule number 3 has a name. It's called Hess's Law. And it works like this. If chemical equation 1 plus chemical equation 2 is equal to chemical equation 3, then delta H for equation 3 is going to be equal to the sum of the delta H's for equations 1 and 2. So it is often used to calculate delta H for one step, knowing delta H for other steps and the overall reaction. So I think we've seen this before, that many reactions actually happen in steps. Let's look at one example. The combustion of solid carbon, let's say charcoal, or diamond maybe. The combustion of solid carbon in oxygen actually proceeds in steps. In the first step, one carbon atom combines with one oxygen atom to make carbon monoxide. And let's say that we don't know what delta H for that is. In the second step, a molecule of carbon dioxide gas combines with another atom of oxygen. Yes, 1/2 O2, that just means 1/2 a mole. Okay, so I'm talking here in terms of atoms, but this is moles as well. So 1 mole of carbon, 1/2 a mole of O2 makes 1 mole of CO. 1 mole of CO plus 1/2 a mole of O2 produces a mole of CO2 gas. So we basically just added another oxygen atom onto there, and we'll call this delta H2, and let's say that we know that this one is 283.0 kilojoules, and that's what it is. And then let's say we know the overall reaction. So overall we have carbon solid plus a whole mole of O2 yields a mole of CO2. And let's say we know that delta H for that is negative 393.5 kilojoules. So first of all, satisfy yourself that equation 3 is the sum of equations 1 and 2. Carbon shows up here and it shows up down here. How come there's no CO in this final equation? Because the CO cancels out, because it's the same on both sides. And then why is there 1 mole of O2? Because we had 1/2 and 1/2 here, and then we only have 1 mole of CO2. So we just added 1 and 2, and what we got is equation 3. Now, using Hess's law, what we're saying is that negative 393.5 kilojoules is equal to negative 283.0 kilojoules plus delta H1. And so we can solve for delta H1, and we find out that it is negative 110.5 kilojoules. Now, why don't I, just to make sure you get this, the units here, why don't I say kilojoules per mole here? Well, because you might say, all right, well, that might work for equation 1 if I mean per mole of carbon, but it's not per mole of oxygen. So you got to be careful. It's actually for 1/2 a mole of oxygen, 1 mole of carbon producing 1 mole of carbon monoxide. So I'm not using kilojoules per mole in this case. So that's an example of using Hess's law. All right, now I want to do one that's a little bit more complicated with Hess's law. Because these do get a little bit more complicated. And this will actually pull in the previous two principles as well, the previous two rules. Okay, this problem says, given the following two reactions and enthalpy data, calculate the enthalpy change for the reaction in which methane and oxygen combine to form CH2CO and water. So let's look at the reactions. Here we've got, and this is called ketene, CH2CO, and this is forming, it's reacting with oxygen to make CO2 and water. And delta H for that is negative 981.1 kilojoules. And then the other reaction they give us is methane, combustion of methane, to produce CO2 and water. And making delta, and delta H is negative 802.3. And what they want us to get is the reaction in which methane and oxygen combine to form ketene and water. So let's call this 1, call this 2, and then 3, the reaction of methane and oxygen to form ketene and water. Now you can see that this is not either of the above reactions. First of all, let's balance this and make sure we've got this okay. Okay, we've got two, we're going to have two methanes here because we've got 2 carbons. It's going to give us 8 hydrogens, so we probably want, we've got 2 hydrogens here, so we'll make this 3. That'll be 8 hydrogens. And then the oxygen is going to have to be 2. Right. Okay, so this looks good so far. So what we've got to do is we've got to be careful here because we can't just add these two, because right now the top 2 equations will not sum to give us the third. So what we have to do in a problem like this is we have to manipulate equations 1 and 2 so that when we add them together we'll get equation 3. The first thing you want to recognize is that the ketene, the CH2CO, is on the wrong side in equation 1. So what I'm going to want to do is I'm going to want to reverse equation 1. So let's do that. Let's say reverse equation 1, and that's the first step. So I'm going to have 2 CO2 gas plus H2O gas yields CH2CO gas plus 2O2 gas. Now, according to rule number 2, rule of thermochemistry number 2, this is going to simply change the sign of the delta H value. Now notice that I have CH2CO on the correct side now, and I have only one of them, so I'm pretty happy right now as to what I've got. But let's look at the second one. The second equation's got a problem because I have 2 methanes in my final equation, but only 1 methane in equation 2. So all we're going to do is multiply by 2 for equation 2. So we're going to write equation 2 times 2. So that's 2 methanes, 4 O2s, yields 2 CO2s, and 4 H2Os. And then the delta H, according to rule number 1, we're simply going to multiply delta H by 2. So in this case, that's 802.3 times 2. Which is 1604.6, and that's negative. I didn't change the sign this time because I didn't reverse the reaction. Now when we add these two together, we should get 2CH4. That's right. What happens to our CO2? CO2 is going to cancel because it's the same on both sides. This H2O is going to cancel, and this is going to change to 3H2O. This oxygen is going to cancel, and this will change to 2O2. And that gives us exactly what we were looking for right here. And now we have only to add these two up. So 981.1 minus 1604.6 should give us negative 623.5 kilojoules. All right, so hopefully you'll get some more practice with problems like that. Now, the next topic is very important, and that is heats of formation. Now, the heat of formation is really based on Hess's law, and I'll mention a little bit more about that in a minute. But the symbol for the heat of formation is delta H subscript F with a little naught symbol there, which means standard conditions. Heat of formation under standard conditions of a compound is delta H when 1 mole of the compound is formed from its elements in their standard states. Now, before we move on, let's make sure you know what an element is, first of all, right? And let's talk about standard states. For most elements, their standard states, so for example for metals, let's say for most metals, the standard state is simply monatomic. Well, it's not really monatomic. They're in metallic bonds. Usually it's not a single atom, but we write the standard state as one atom and with a solid, because under standard conditions, 25 degrees C and 1 atmosphere of pressure, and that's what this indicates. That's the state of most of these. And if it were zinc, it would be the same. If it were copper, it would be the same. Silver, and so on. Now, there's a couple exceptions. Of course, we've got mercury is a liquid, right? That's really the only exception, actually. So that's why I say for most metals they're solids. But when we're dealing with nonmetals, we get some more curious behavior, and it gets a little bit more complicated. And we get a whole bunch of them that are going to be diatomic in their standard states. Diatomic gases or liquids. And we've got nitrogen, oxygen, and fluorine. Those are all what we call diatomic. So in their standard states, they're going to be forming molecules made of 2 atoms. And so we need to write them like that whenever we're writing equations with these. And then as we go down the halogens, so I'm going across the periodic table here. We've got chlorine gas, bromine to liquid, and then iodine to solid. The noble gases are all monatomic. Okay. Now we need to watch out a little bit. Sulfur is a solid, and it's S8, which is kind of weird, and phosphorus in its standard state is P4, solid. So you should memorize these, in particular these diatomics and then sulfur and phosphorus, so that you know how to recognize when they're in their standard states, because that's going to become very important, recognizing an element in its standard state will become very important, because delta H of formation for an element in its standard state is 0. Okay? And that's why it's important to be able to recognize the standard states of elements. So let's look a little bit more at this idea of heat of formation. Let's say we take 2 moles of silver, combine it with chlorine gas, and get silver chloride. And let's say that delta H for that reaction under standard conditions, that's what the little naught means, is negative 254.0 kilojoules. That means that delta H of formation for silver chloride is negative 127.0 kilojoules, which is 1/2 of that. Why 1/2? Because that was negative 254 was for 2 moles, and this is kilojoules per mole when we write the heat of formation. We've seen this before. Mercury oxide. Now notice I've written it a little bit differently here. I wrote 1/2 mole of O2, and so this is going to be 90.8 kilojoules. And what we could say then is that delta H of formation for mercury oxide is going to be negative 90.8. Oh, why negative? Why is it negative? Remember that the decomposition of, sorry, this should have said mercury oxide. The decomposition of mercury oxide absorbed heat energy. Well, remember, we're talking about the formation. So this is for the decomposition. But what we're interested here is the formation. Okay, so that's the basic idea of heat of formation. Now, what is it used for? Use of delta H of formation. Generally, we're going to use it with this equation. We don't really have a name for this equation, although it is actually, you can show that this can be derived from Hess's law. The heat of formation of the products minus the heat of formation, of the reactants. And this, of course, is the sum. So the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. And remember that elements in their standard states are taken to be 0. The basic idea here is you can think about any reaction as consisting of breaking down the products and then forming the reactants. And if you and we've talked about that in the previous lecture. If you take that and then combine it with Hess's law, you get this equation. Now first, I think before we go on, I want to show you a table of standard enthalpies of formation, what it would look like. Standard heats of formation, enthalpies of formation. Notice over here, so they've got and there's a table like this in your textbook, and it is on page 241 in your text. This is from Wikipedia here. And notice that these are all the delta H formation in kilojoules per mole. A lot of them are negative, but not all of them. And you can see here table salt, solid, liquid, gas. So this is important. You got to be careful of what phase you're in. Remember, there's something called delta H of fusion and delta H of vaporization. Those are required to change a substance from between states, to convert between states. And so the state matters big time in these calculations. So this is where you would get the heats of formation, the delta H of formation values. And the nice thing is there are tables and there are sites like wolframalpha.com where you can get the heat of formation for just about anything, just about any compound you would want. Using this equation, you can figure out the heat of formation for all sorts of different reactions. Using this equation and a table of heats of formation, or a site like Wolfram Alpha, you can get the heat of reaction for many different reactions. Again, that means the summation. So let's look at an example. CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O liquid. And we want to know delta H. So here's the question. What we do is we look up in a table. And if I look up a table, now I don't think, let's see if I have methane in here. It looks like I don't, probably. No, I don't have the heat of formation for methane. But if I were to look it up, say in my textbook, I would find that the heat of formation for CH4 gas is that 241 I said, so I'm looking at page 241 in my textbook, and I see that heat of formation for methane is negative 74.8, the standard enthalpy of formation, negative 74.8 kilojoules per mole. Now the heat of formation for O2 gas. Okay, so I'm looking up the delta H for O2 gas, but I don't see it on here. Why is that? Because it's 0. That's right, 0 kilojoules per mole, because O2 gas is an element in its standard state. Delta H of formation for CO2 gas, however, is on the table, and so that is negative 393.5. That number should look a little bit familiar from this lecture, and that's per mole. And then delta H formation for H2O liquid. Be careful, make sure you're looking at H2O liquid, because they're going to include liquid, solid, and gas on there. It's negative 285.8. Now this is not for boiling or melting water. This is for forming water from hydrogen and oxygen gases. Now, applying this information using the heat of formation equation here, it's the sum of the heat of formation of the products. Okay, so it's going to be the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So what are the products? Well, it's 1 mole of CO2. So I've got 1 mole of CO2 times, notice I'm multiplying by the moles here, negative 393.5 kilojoules per mole, plus, because I'm summing up the products, 2 moles H2O times negative 285.8 kilojoules per mole, and then I'm going to subtract the heat of formation for methane. Subtract 1 mole of methane times the heat of formation, which is negative 74.8 kilojoules per mole. Be careful with the signs on these. This gets really, it can get really pretty tricky. What I end up with here, of course, is negative 393.5 kilojoules plus 2 times negative 285.8 kilojoules plus 74.8 kilojoules because I've got a minus a negative here, and that gives me negative 890.3 kilojoules, not kilojoules per mole. My moles cancel, 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 cancel. Okay, so the answer to this is negative 890.3. Now, it can also apply to ions. reactions that include ions. So we've got the only thing you have to remember here is that the H plus ion in solution is assigned a delta H of formation equal to 0, just like it were an element in its standard state. So let's take a look at something like this. We've got solid zinc plus 2 H plus ions, so zinc reacting with an acidic solution, and it's going to produce zinc ions, so the zinc will dissolve in the acidic solution and it'll produce hydrogen gas. Now this becomes a pretty simple calculation because the delta H is simply going to be equal to the delta H formation of the zinc 2 plus ion, aqueous zinc 2 plus ion, which is negative 152.4, and I get that from a table. Why? Because this is 0, this is 0, and this is 0. See how that works? Okay, I want to look at an example before we move on to bond enthalpies, and I want to use the example of thermite. And first start by showing you a quick little video of a thermite reaction. It's from the periodic table of videos. Aluminum and iron oxide.
Talk me through what's going on, mate.
So instantly the thermite reaction starts, and you can see that it's so hot it's burnt a hole through the bottom of that terracotta flower pot. But if we go in close now, Brady, you can see all that really quite nice molten iron. Now that's so hot that the iron itself has melted and it's formed.
Now that's a very exothermic reaction, and it is simply, it's really pretty simple. It's just the reaction of elemental aluminum in its standard state with iron oxide. There are actually different kinds of thermite. You can make it with magnesium also. And this stuff has historically been used for welding even. You can actually like carry this thermite powder with you, and let's say you're working on the railroad and you want to weld rails together. This stuff will do that because it produces molten iron, as they showed in the video. And the reaction for this is 2 moles of aluminum, solid aluminum. And you got to hold me to this. I've got to show you this in person here. So remind me of that, because we can do this in the lab. We do a little bit smaller scale so we don't make as much of a mess. We don't want any molten iron burning its way through our countertops, which it would do, by the way. It'll burn a hole right through thick plate steel if there's enough of it. Very exothermic reaction. This is the reaction here. Basically, it's what would be called a single replacement or a single displacement reaction, with the aluminum replacing the iron in the oxide. And we've got delta H for that reaction under standard conditions being negative 851.5 kilojoules. So that's a substantial amount of heat being given off, and it is enough heat to result in liquid iron at the end. Now what I want to show here is just the basic process of calculating delta H. So using the equation there that we just learned how to use. So we know that this is going to be 0 and this is going to be 0. So all we really need here is delta H is simply going to be the delta H of formation for the aluminum oxide minus the delta H of formation for the iron oxide. So you can kind of see here, if you wanted to make a better thermite, a more efficient thermite, say you wanted to try using zinc instead of aluminum, or magnesium instead of aluminum, or sodium, or something like that, you could just look at the oxides, the heat of formation of the oxides, and the bigger the difference in the heats of formation of the oxides, the bigger the yield of heat for your reaction. So let's look at our table on 241. I'm going to look up the heat of formation of aluminum oxide, which is negative 1675.7. And we have a mole of each, so I should have written in the moles. here. Sorry about that. And the heat of formation of iron oxide is going to be not shown. Oh, there it is. Fe2O3 solid, negative 824.2. Notice I haven't shown the moles here because I'm really multiplying by 1 mole, so I've canceled them out. So it's 1 mole times this, and then 1 mole times 824.2. And when I do the calculation, I should get negative 851.5 kilojoules. Okay, now here's a question that we could ask. Is this enough heat to melt the iron? Now let's we're going to have to simplify this a little bit, because any substance is going to have a heating curve like I drew earlier for water, where you heat up the solid, you melt it, you heat up the liquid, then you boil it, and then it's a steam. And so we're going to assume here we need the heat of fusion for iron, and we're just going to look at this point right here. We're not going to worry about heating the iron up, which would just, this portion of the graph, the sloped portion, that would be a Q equals MC delta T calculation. But we're going to leave that out for now. And we're going to ignore that. We're just going to go and look up the heat of fusion for iron. Let's see what we get. Latent heat of fusion. Yeah, sometimes it's called the latent heat of fusion. And let's see. Kilojoules per kilogram. Okay, so they don't give it in per mole here. For iron, that is 272 kilojoules per kilogram. So 272 kilojoules per kilogram. That's what's required to melt the iron. So what do we have here? We've got 1 mole of iron, which is, a mole of iron is a lot less than a kilogram. It's only 55.85 grams. So for 55.85 grams, or do we have, sorry, we have 2 moles iron, so 2 times that. We have 2 moles of iron, and then, so what we're going to do is we're going to convert that to kilograms, and then we're going to change that to moles. Oh, sorry, we don't need to do that. We're going to convert that to kilojoules. So we've got 2 times 55.85 divided by 1,000, and then times 272. So we need 30.4 kilojoules to melt it. And what did we produce? We produced 851.5 kilojoules. So you'll bet we've got enough. So we're going to melt that iron, and it's going to burn right through whatever container we've got it in, and it might keep going. So that's why you notice in the video they had it fall into a container of sand. Alright, last topic in this chapter is called bond enthalpies. Now we won't be doing a whole lot with these, and I'll tell you why in a few minutes. But there's a nice table of bond enthalpies in your book, and so take a look at that. It's on page 247. And it's set up so that it has like elements listed across the top and the same elements listed down the side, and so you can figure out a single bond between any 2 elements on that table. You can figure out what the enthalpy would be. And what we're talking about here is the bond enthalpy is delta H when 1 mole of bonds is broken in the gas state. Now, from the previous lecture, you will know that this is always going to be positive because breaking a bond always requires energy. So let's look at an example. If we want to break the chlorine to chlorine bond, and it's in the gas state, delta H is simply going to be equal to the bond energy of the chlorine to chlorine bond. And you can find that in the table on page 247. I look at chlorine and I trace it down to chlorine and I see that it is 243 kilojoules per mole. And in this case, because we've only got 1 mole, it's just 243 kilojoules to break those down. And let's look at another example. Now, triple bonds, I mean, there's multiple bonds here, so you might guess that they would take more energy to break down. The bond energy, and this is kind of a separate part of the table there on page 247, the bond energy of the triple bond between the nitrogens is 941 kilojoules. And in general, multiple bonds are stronger than single bonds, and you will see that in the table. Now, you could use this to calculate bonds, but you have to be a little bit careful. It would work really well in if you were just dealing with diatomic molecules. So let's take an example here. Let's look at the H2 plus Cl2 yields 2HCl. Now, can you see how we could use the bond energies to figure out the delta H for this reaction? Of course, we could use heat of formation because this is simply twice the heat of formation of HCl. These are both elements in their standard states. But what if we use the bond energy? Well, first of all, since we don't have our book in front of us, the hydrogen to hydrogen bond energy is, looking on that table, is 436 kilojoules per mole. The chlorine bond energy, chlorine to chlorine single bond, is, as we saw up here, 243 kilojoules per mole. And the bond energy of hydrogen to chlorine is going to be 431. So to calculate this, we've got to think about it like this. We're going to be forming 2 moles of HCl. So on this side, so we're forming 2 moles of HCl. So what's going to happen is delta H for that is going to be twice 431, but it's going to be negative. So it's going to be it's going to be negative 862 when we form 2 moles of HCl. We're going to be breaking a mole of each hydrogen and chlorine. So this one's going to be positive 436 kilojoules, and then the chlorine positive 243 kilojoules. Now what we can say is that these are really just happening in steps. All right? And so we can add them all together to get the sum of the whole thing. So we're going to break these, we're going to break these, we're going to form these, and let's see what we get. So we've got 436 plus 243 minus 862 negative 183. Let's scroll back and see if that's what we got earlier. Where was that? Oh, it's off a little bit, and who knows why that is, but it's off a little bit from that. We don't typically use these tables of bond energies to actually calculate delta H, and one reason is, and it doesn't really apply here, but if there's something else bonded to the atom. So, for example, in a case like this, the bond energy between each hydrogen and chlorine is going to be a little bit different than it would be in a case like this, if it were just 1 to 1. The presence of the other atoms bonded to the same central atom is going to change the bond enthalpy. So it all gets very complicated when we get into more complex molecules. So we won't generally be using the bond energy. All right, now I'm not going to cover the last section, the first law of thermodynamics. We don't typically cover that, but I do encourage you to look at that, at least 8.7, and be familiar with it. Section 8.7, the first law of thermodynamics. When we first started out, we said that delta H is equal to Q at constant pressure. All right, and this section deals with situations where that is not the case. So in confined systems, what we typically do is, instead of looking at delta H, we look at the total change in energy, and it's the sum of the heat and the work done by the system. It's the sum of the heat and the work that is transferred between the system and its surroundings. All right, and not real complicated, but definitely just take a quick look at that. All right, I hope you enjoy the rest of your break.